Hello. This podcast is on force pairs and Newton's third law. Specifically, we're going to learn what action-reaction force pairs are, how they apply to Newton's third law, and lastly, we're going to learn how to identify action-reaction force pairs in real-life situations. Let's get started and learn about force pairs. We know forces are interactions between two objects. One object exerts the force and the other object receives or feels the force. But there's more to forces. Forces always occur in pairs. There'll never be just a single force. So let's take a look at this person pushing against the wall. Every force causes another force. So this person pushing on the wall causes an action force, and as a result, the wall pushes back on the person, and we call that the reaction force. And together they are called an action-reaction force pair. So the person pushing on the wall and the wall pushing back on the person are known as an action-reaction force pair. They do occur simultaneously. So while I'm calling the person pushing on the wall the action force and the wall pushing back on the person the reaction force, they happen at the same time. One does not come before the other. So picking which one is the action force and which one is the reaction force is your choice. You get to choose. Let's take a look at some examples. So this skateboarder is pushing on the ground, and the reaction force is the ground pushing back up on his foot, and that's what makes him and the skateboard go forward. Here's another example. We have a book sitting on a table. We know that the table is pushing up with a normal force on the book. The reaction force to that is the weight of the book pushing down on the table. So both are normal forces, the normal force of the table pushing up on the book and the normal force of the book pushing down on the table. Let's take a look at one more example. Here we have a guy in a boat beside the dock, and so he steps forward onto the dock. That creates an action force of friction, the friction of his sneaker pushing back on the boat, and the reaction force is the surface of the boat pushing forward on his sneaker. Let's look at a few more action-reaction pairs, and this time you see if you can figure out the reaction force. Here we have a car, and the action force is the tire pushes on the road. That's this force. What's the reaction force? Well, it's the road pushing on the tire, and that's this forward or rightward force. Let's do another one. The action force is a rocket pushes on the gases. So the rocket is pushing the gases out the exhaust tube. What's the reaction force? Well, it's the gas pushing on the rocket, and that's this force pushing the rocket forward. And that's how rockets are launched, whether it's just into our atmosphere or up into outer space. The gases that exhaust from the rocket have pushed forward on the rocket because the rocket has pushed backward on them. Let's do another one. The action force is a man pulls a spring, so this is the action force. The man's pulling the spring backward. The reaction force is the spring pulls the man, so the spring is pulling the man to the right. And one more. We have the Leaning Tower of Pisa, and this person's dropping a ball off of it, and the action force is the Earth's gravity pulls on the ball, so this is the action force. What is the reaction force? This one's a little tricky. The ball is pulling up on the Earth, so the ball is exerting a gravity force on the Earth and pulling the Earth up. Of course, to us, we just see the ball falling. We don't see the Earth moving up, and that's because the Earth just moves a teeny bit, much smaller than we or any instrument could detect. Let's talk about Newton's third law of motion. Newton simply stated, for every action, there is an equal and opposite reaction. So let's take a look at an example here. We have our action force, and that's the person pushing on the wall. So for every action force, there is a reaction force, and that would be the wall pushing back on the person. These happen simultaneously, so even though we call one the action and the other the reaction, they happen at the same time. They are equal in strength, and they are opposite in direction. So that's what Newton means when for every action there is an equal and opposite reaction. Forces happen simultaneously in pairs that are equal in strength and opposite in direction. Let's move on and learn how to identify action-reaction force pairs. And just to let you know, they're also sometimes referred to as Newton's third law pairs or Newton's third law force pairs. Well, there are three characteristics that all action-reaction force pairs must have, and they have to have all three of them. They just can't have one or two of them. They have to have all three of them. So one of them, they must be the same type of force. If the action force is gravity, then the reaction force must also be gravity. If the action force is a normal force, then the reaction force has to also be a normal force. 2, they must be equal in strength and pointing in opposite directions. So if the action force is a 500 Newton force in the positive direction, then the reaction force must be 500 Newtons in strength and in the negative direction. And lastly, they must involve the same two objects. If the action force is the Earth's force of gravity acting on the person, then the reaction force must be the person's force of gravity acting on the Earth. So see, it's the same two objects for both of these forces, the Earth and the person and the Earth. So the objects are the same in an action-reaction pair, it's just that their roles are switched. In this first force, Earth is acting on the person, and in the reaction force, the person is exerting the force on the Earth. One final important point, action-reaction pairs will never be on the same force diagram. You need to draw a force diagram for both objects in order to find the action-reaction pairs. And sometimes you'll have to draw a force diagram for more than two objects. Okay, let's do some practice. We have a boy jumping on a trampoline. So the first thing we have to do is draw a force diagram for the boy and a force diagram for the trampoline. So for the boy, or I'm calling him the person, we have the force of gravity pulling down on the boy, and we have the normal force of the trampoline pushing up on the boy. Then if we look at the trampoline, we have the force of gravity pulling down on the trampoline. We have the normal force of the Earth pushing up on the trampoline, and we also have the normal force of the boy pushing down on the trampoline. So let's look for the action-reaction pair, and let's remember the three characteristics they have to have. First, it needs to be the same type of force. So here we have a normal force. That means over here we need to be looking for a normal force. Well, we have two normal forces. So let's go to our second criteria. They need to be equal in strength and opposite in direction. Well, that rules out this normal force because this is pointing up and this force is pointing up. So this normal force of the Earth pushing up on the trampoline cannot be the reaction force. Let's take a look at the remaining normal force. It meets our second criteria, which is that it's pointing in the opposite direction and in equal strength. Let's see if it meets the third requirement. It needs to involve the same two objects, but their roles are reversed. So up here in what we identified as the action force, we have the trampoline and the person, and the trampoline's exerting the force. Down here, this normal force also involves the person and the trampoline, and now the person is exerting the force on the trampoline. So these two forces create an action-reaction pair. Doesn't matter which one you call action and which one you call reaction. Now let's look at this other force here, the force of gravity, the earth acting on the person. Let's see if we can find a reaction force for that. So our first criteria, it needs to be a gravity force. Well, we have a gravity force over here. Let's go to the second requirement. They need to be equal in strength and opposite in direction. Well, here we see that they're both pointing down, so they're not opposite in direction. Also, we know that the trampoline weighs more than the boy, so the Earth's force of gravity on the trampoline is going to be much stronger than the Earth's force of gravity on the person. So the forces are not equal in strength and they're not opposite in direction. And if we look at the third criteria, it doesn't satisfy that either, because in this force that we're calling the action force, the two objects are the earth and the person. And over here, this gravity force involves the earth and the trampoline, so different objects. That's the process you use to try to identify action-reaction pairs. Let's do one more example. So we have a person pushing against the wall. We need to draw force diagrams, one for the person and one for the wall. So here we go with the person. Let's look at our vertical forces first. We have the Earth's gravity pulling the person down towards the center of the Earth. We have the floor pushing up with a normal force that's equal in strength and opposite in direction. Then to the left, we have the wall pushing on the person to the left, and we have the friction force of the floor pushing on the person to the right. Now, if we look at the wall, we have the force of gravity, the earth pulling down on the wall, and we have the normal force, the floor, pushing up on the wall. These forces are balanced. They're in equal and opposite directions. Horizontally, we have the person exerting a normal force or push force to the right on the wall, and we have the floor exerting a friction force to the left on the wall, and that's why the person can't move the wall. Well, let's take a look and see if we can identify some action-reaction force pairs. Let's look first at this normal force, the floor on the person. So we have to go to the other force diagram to look for the reaction force, and we need to find a normal force. Well, we have two normal forces, these two here. Well, I can rule out this one going sideways because it's not in the opposite direction, and I can also rule out this one pointing upward because it's in the same direction as this normal force, so they can't be an action-reaction pair. Let's look at the friction force here of the floor pushing on the person, and let's see if there's a reaction force that goes with that. So if we look over here, we do have a friction force, so it's the same type of force. They are pointing in opposite directions. Now, I don't know if they're the same strength or not, but they're pointing in opposite directions. Let's move on to our third criteria. Do they involve the same two objects? This force of friction involves the floor and the person. This friction force involves the floor and the wall, so they do not involve the same two objects. Therefore, these forces are not an action-reaction pair. Let's take a look at this force of gravity, the earth acting on the person, and see if there is a reaction force to it. We go over here to our other force diagram, and we do have a force of gravity. However, notice it is pointing in the same direction as this force of gravity, not in the opposite direction. So it cannot be an action-reaction pair. Also, if we look at the two objects involved, the earth is involved in both of them, but this gravity force has the person and this gravity force has the wall. So it does not qualify as an action-reaction pair. Let's check our last force on this person's force diagram, and that's the normal force of the wall pushing on the person to the left. So let's go look for normal forces. We have two of them. We have the one pointing up. Well, we can discount that because that's not pointing in the opposite direction. We have this normal force pointing to the right. Well, that is in the opposite direction of this normal force, which is pointing to the left. And let's take a look at our third criteria, the objects. This force over here that we're calling the action force is the wall pushing on the person. And this force over here also involves the wall and the person, but their roles are reversed. The person is pushing on the wall. So these two forces, this normal force, the person pushing on the wall, and this normal force, the wall pushing on the person, are an action-reaction pair because they meet all three characteristics of an action-reaction force pair. Well, this ends our lesson today. I hope you found this information helpful, and have a good day.